Okay, so this is part 3 of the series of videos on Lewis structures. We're looking at compounds or molecules that can be described using multiple Lewis structures. So we've looked at how if there are two possible Lewis structures or more than one possible Lewis structure, how you might decide which one's better. But sometimes they're all equivalent. Good example of a molecule like that is ozone, which you see depicted right here. Ozone's a bit of a weird one. It's got 3 oxygens. So if we kind of think our way through that, each oxygen would have 6 valence electrons. There's 3 of them. That gives us 18 in total. And however you draw ozone, you find to get those 18 electrons, you have to have 1 double bond. You can't have 2 double bonds. That would only be 16 electrons, just 1 double bond. So then you have a choice. Do you put the double bond in this position, or do you put the double bond in this position over here? So that leads us to this concept of resonance structures. Okay, and resonance structures are when as far as IB is concerned, there's a bit of freedom in how resonance structures happen, but as far as IB is concerned, it's when the double bond could go in more than one different place in a molecule. Okay, and what we know about ozone when we look at the data, so using things like X-ray crystallography and by looking at the size of the dipoles, we see that the bonds between the adjacent ozones are actually the same length, which is a bit unexpected if we look at this diagram, because normally we would expect a single bond to be a bit longer than a double bond. Okay, but in actuality, the length of these 2 bonds, so this bond right here and this bond right here, they're the same. And they're a little bit shorter than a real oxygen-oxygen single bond that you would find in a molecule like hydrogen peroxide, and a little bit longer than a true oxygen-oxygen double bond. Okay, so sort of somewhere in the middle. Similarly, if we look at the net charges, we find that the 2 outer oxygens here, rather than this one having a full formal charge of -1, the way it's shown here, and this one having a full formal charge of 0, we see that they both have a formal charge of more of a half. Okay, so these 2 depictions show sort of that symmetrical structure of ozone. So this one is meant to show the symmetrical bonds, and then this one is meant to show the even distribution of charge. So the red regions here represent the negative charge, and then the blue here represents positive. So what we say is that actually just one of those Lewis structures doesn't accurately depict a molecule like ozone. Instead, to give a complete Lewis structures, we have to show all the possibilities. Okay, so if you were asked, draw the resonance structure of draw the Lewis structure of ozone, you should actually include both of these Lewis structures, one with a double bond on the left and the other with a double bond on the right. Excuse me. So one way that we can think of resonance structures is they're like a blend. The actual molecule is like a blend of all the possible Lewis structures that we can draw. So just the way that green is a blend of blue and yellow, an actual ozone molecule is a blend of these 2 Lewis structures. Okay, so this is just a definition of resonance structures, one of a group of Lewis structures used to describe a molecule that cannot be accurately depicted using a single Lewis structure. Now, it can be really tempting to imagine that in the actual molecule, the electrons are sort of flipping back and forth between the 2 possible positions. That's not really the case. And I mean, to really understand this, you need, it goes kind of beyond the scope of our course. You need a good understanding of like molecular orbital theory probably, but the actual molecule really is a hybrid of the 2 Lewis structures. The Lewis structures are just a way of representing it. Okay, but if we look at the actual properties of the bonds and the charges in the molecule, it is a blend of those 2 Lewis structures. And then just to remind you of the language that you see in the chemistry guide, because often IB really does want key terms that show up there. So resonance structures occur when there is more than one possible position for a double bond in a molecule. Okay, and that's it about resonance structures, except I'm obviously going to go through an example. So here, my suggestion is the nitrate ion. And really what I think you should do right now, pause the video, draw one Lewis structure of the nitrate ion, just it's good practice, and then see if you can figure out from the one what the other two Lewis structures would be. So you should only have to go through the whole process of drawing a Lewis structure once, and then you should be able to see how you can move the double bond around to get the three versions of nitrate. So take a pause, give that a try. And welcome back. Hopefully you got something that looks like this. So you total up the valence electrons, 5 from nitrogen, 6 from each of the 3 oxygens, and then because it has a negative charge, you add one more to get 24. So it doesn't really matter which one you draw first, as long as you have a double bond in that nitrate ion, and then in the other resonance structures, you just move that double bond around. Okay, and making sure to observe the octet rule each time you move that double bond around. So, for example, this oxygen, or the oxygen making the double bond, has 2 non-bonding pairs on it. And then the oxygens with single bonds have 3 non-bonding pairs. Also, don't forget, because it's an ion, you need those big brackets and then a negative charge. Here's another example of a molecule that comes up often that has resonance structures. So this is benzene, and we're actually going to talk about benzene quite a bit more when we get to the organic chemistry unit next year. But benzene, it's a really common organic compound. It is a ring with 6 carbons, and then there are these alternating double bonds. So each carbon is single bonded to a hydrogen, and then double bonded to one carbon, single bonded to the other. But it doesn't really matter where those double bonds would be. We would maybe say that in this version, they're in the 1, 3, and 5 position, and in this one, they're in the 2, 4, 6 positions. Okay, but it really doesn't change anything else about the molecule to move those double bonds around. So these are resonance structures. And we actually see, so this is a Lewis structure representation right now, but in organic chemistry we often take shortcuts in the way we did pick the molecule. So this is a sort of an example. It's called a skeletal diagram, and then often we'll see benzene represented this way with a circle in the middle to represent the resonance rather than having to draw 2 versions. Okay, so that's just a description of what this is right here. Hexagon with a circle. And then these electrons, because we say that they can move around, a word that will come up often to describe them is delocalized. So the electrons in the double bonds are delocalized. They can be between these 2 carbons or between these 2 carbons. Okay, let's put a pause there. Resonance structures, and then we will do one final video, part 4, that deals with exceptions to the octet rule.